Hello and good afternoon. Um, okay, so we will be talking about operating system concepts. So continuing the second lecture, and if you guys have questions from the previous lectures, please use the Q&A. Okay, so somebody is asking a question, are we not using the makeup lecture tomorrow? No. So again, everything that we're using will be on the course website. So the one that we're using tomorrow is just the tutorial. The makeup sessions, just for your reference, they're marked. We will have two of them. So the one is here, Friday, February 11th. So that's one makeup session, and the second one will be on March 4th. So these are the two makeup sessions that we'll use, because we'll lose two sessions on during the midterm week. So that's why we have two makeup sessions scheduled. Okay, so let me just very briefly talk about the course project. Lab 1, and then I'll go back to the lectures. So, okay. So in Lab 1, you are supposed to write a memory management unit for your RTX. So when your operating system, oh, this is too, okay, let me see. Let's go 100%. Oh, this is better. Okay. So, okay, when operating system is booted and loaded, then so from address 0 something to end of this, I'm gonna just call it address X. So in the lab manual, we actually mention what that is, but here is your OS image. And here's the end of RAM that you can access. So we provide macros for that. Seems like the internet connection is a little bit bad, so sorry for that. Now, let's say somebody does this, void star P1 equals kmem alloc, let's say 10. Okay, so you're going to come to this address. This is the beginning of your memory management unit. You hopefully have you have set up this when you called kmem init to initialize this free memory. You know, at this point, you want to allocate this 10 bytes. You probably will put some stuff here. You say, you know, you're logging for yourself. You say a bit larger. Yes, sure, I'll try. So you say, you know, this is the net, you know, you log here with your data structure. I'm just, you know, putting the overview here. You say the next 10 bytes are allocated. And probably you want to, you know, have a pointer to, you know, after this 10 bytes. So these are the 10 bytes that you're going to allocate. This is your metadata. Sorry, I still wrote small, but what about this? So this is your metadata, right? And then you have that 10 bytes. You probably here the address that you return is going to be this address. So you return this address, the beginning of this 10 bytes. Then let's say later on you do another one, void star p2 equals k mem alloc, let's say this time 20, right? Now again, you're going to come to the beginning of your data structure and say, oh, here I have logged it that 10 bytes are allocated, and I know a pointer to the beginning of the next free memory unit, which is here. So you come here, you say, oh, I have a lot of memory to allocate. So I'm going to put my metadata here. I'm going to say another metadata. Probably I want to say the next 20 bytes are allocated, and potentially put a pointer to the next free space. Right, so here is your 20 bytes, and then you return a pointer to the beginning of this 20 bytes to the user. Now, let's say time passes by, and then you say, okay, I'm done with my memory, deallocate, kmem dealloc p1. So when this happens, the operating system is going to come here and say, okay, this unit is no longer needed, so I'm freeing it up. But I, again, probably want to put some metadata here to say that the next 10 bytes are free, right? So this becomes free, and this area is still free. So probably I still need some metadata here to say this is free, and probably, you know, I want to update my pointers and say that, you know, this one is free, and then the next one free is here. Now, time passes by, and you may actually then do P1. This time is k mem alloc 30. Now, when you see this guy, you're going to come to your memory and say, oh, I have free stuff here, but it's only 10 bytes. So I can't fit this 30 here. So I'm going to leave it empty, and instead go and use the free memory here and put metadata here and allocate 30 bytes. And then I have my free stuff here, and probably I want to update this pointer and say next free stuff are here. Now, if you then look at your memory after a while, you probably will see something like this. A bunch of it is allocated. There's free space, there is allocation, free space, allocation, again, free space, allocation, so on and so forth. So after a while, your memory becomes defragmented. It becomes fragmented. So this is normal, right? And you probably, the OS needs to know the pointer to all these free spaces, right? Whenever it wants to allocate, it wants to know which parts are free, which parts are consumed or being allocated. And probably for all this tracking, the operating system needs to hold some, or, you know, store some metadata. Now, the free space, sorry, the allocated space is usable for your user processes. So these, this 30 byte, this 20 bytes, initially when we allocated the 10 bytes, they're all free. Sorry, they're all usable by the user program. But these metadatas, these are spaces that we use for metadata, and probably some here. So the metadata is a space that the operating system is using for itself. So operating system is using some of the free memory to keep track of it. So this becomes the overhead. So all these, pieces of data that the operating system is keeping for itself to track what is allocated, what is free, becomes the overhead. And everything that we have allocated becomes usable. So after a while, I can say, let's say I fill up the memory, the entire memory. I can look at how much I actually allocated and how much metadata operating system has used. And then my utilization becomes what I have allocated divided by how much memory I had, because the rest of it is overhead that the operating system has consumed. So hopefully this gives you an idea. Now, the algorithm that I described here, where every time we get a request, we start from the bottom of this list and we search for space to fit, is called first fit algorithm, obviously. There are other algorithms, as you can actually look into the document that we have cited in the lab manual. You can look at all the other types of memory allocations that you could potentially implement. And first fit is very simple, but as you can see, it's kind of time consuming. Every time you want to allocate, you basically have to do a link. You have to do a search from the beginning. You have to look at this free space, see if it fits. If not, you go to the next one, you go to the next one, you go to the next one, until you find some place to fit your allocation. So it's simple, so it's good for implementation, but it's probably a little bit time consuming in terms of performance. So there are other allocation mechanisms that are, a little bit more complex, but then they give you better performance. But we didn't want you to implement the more complex ones, like the body algorithm. So we're gonna stick to this one. Let's see if you guys had any questions. So would it be possible to write a bit larger? Hopefully, I did it. Maybe I didn't. Sorry. I can do this. Okay, so would the metadata be part of the overhead? Metadata is the overhead, right? Anything, any memory that the operating system is using for itself, for its tracking inside the heap, is considered overhead. And anything that the operating system gives, a pointer to the program to be used by the program becomes the usable memory. Would it be okay to put all metadata in a single spot? This is a design choice. Do it the way you want, right? There is no requirement on how you implement this. So if you come up with a design where all the metadata sits somewhere, go ahead, do it the way you want. So I'm not going to say anything more. So this is a design choice. For how much metadata you need. How do you want to keep track? Do you want to have a linked list? Do you want to have all, others lists? Do you want to, have it double linked, one-sided link? These are all your choices. Make your choices wisely how you want to implement this. But it's up to you. The way you wish, you can implement it. If as long as it meets the requirements that are specified in the lab, you should be fine. Okay, will we also be coalescing while calling fmem-free to deal with fragmentation? Yes, that's a requirement that you can see in the lab manual. So what is coalescing? So let's look at this example here. Let's assume that, you know, the user comes and says, free this memory for me. If we want to free this memory, now there is a free memory here already. And if I want to free this memory, I need to coalesce this two to get one big chunk of, gosh. So yeah, so if I do free this memory, I need to coalesce this two to then have a bigger free memory. So I have to say, okay, now I have this much free to be allocated. And you do this when you free a part of memory and then you see, you know, there were neighboring regions that were free, so you can just join them all to have one big free region. So once more, overhead equals size of metadata divided by size of actual allocated data. No, overhead is overhead any memory OS uses for its tracking. That's overhead. So let's say I have, you know, just for an example, let's say I have 100 kilobyte, and let's say, you know, I do, you know, I allocate, let's say 10 kilobyte. So this is my 10 kilobyte, and this is the metadata that OS uses. Then I do another 5 kilobytes, let's say. So this becomes my 5K, and this is a metadata, or whatever you want to name it. Then let's say I allocate 50K. So like it gets like something like this. And then some metadata here. And then let's say I do another 40, and sorry. And let's say at this point I fit every, oh, I can't do 40. Let's say 30. So let's say at this point the memory is full. So now what is the utilization? What is the utilization? The utilization is how much memory do I have? Did I have in total? I had 100 kilobyte. This was my free memory. How much I did end up allocate? Well, I allocated 10 plus 5 plus 50 plus 30. So I allocated 95K. So my utilization is 95% for this particular benchmark, right? So this is one benchmark. I could have another benchmark where I allocate just 1K, 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 and for each 1K I incur some overhead for the metadata, and my utilization is less, right? But for this one, this particular benchmark where I allocated 10, 5, 50, 30, and at that point my memory got full, I couldn't allocate more. So at this point, my utilization is 95%, meaning that out of this 100K, I can use 95K. The rest of it, operating system is using for its tracking, and I cannot use it. So this becomes my utilization. Hopefully that is clear. Okay. Now let's go back to the lecture. Okay, so we talked about virtual address space layout for a C program. Somebody was eager to ask me about execution stack in the last lecture. So here comes execution stack. So what is a stack used for? Mainly for two purposes. One, to keep track of where we want to return after the function is. So we're using a stack for function calls. Let's put that into rest. So the main use of a stack is for function calls. Now, what do we store on the stack? We store local variables and inputs. We also store return addresses. So let's look at this example. In this example, I have three programs. So I have three functions, sorry, function A, function B, and function C. This is kind of like a nested function call. So C calls A, sorry, A calls B, B calls C, and then C calls A, right? So it's kind of like nested function calls. Let's say A1, A0, A1, A2, B0, B1, B2, C0, C1, C2. These are annotations for those lines. We're going to use them as addresses. Let's say PC is here. So program counter is here. We want to execute this line. The first thing that we're going to do is, well, this is time for us to use a stack because we have a function to be called. Now, as I explained, we need to push things on our stack. What do we push? We push variables. We push return address. So this A function has this variable temp as an input. So we're going to push that. When we're here at this point, this is going to be 1. So we push this input on the stack. We also push the return address. We want to say once we're done with A, where are we going to go? So if PC is here, then the next line is ext. So next, the return address, once we're done with function A, we want to come to ext. So that's why we push return equals ext on the stack. So this is how our stack will look like right before we jump to function A. Now let's jump there. The PC becomes A1 when we go to execute function A. We check temp. Well, where is temp? Temp, where are we going to find temp? We're going to find temp on the stack, right? Anything inside our functions, we're going to look at them inside the stack. Although if your function uses global variables, then you use the global variables addresses. It's not going to be on your stack. As we saw, global variables reside on top of the bytecode, so they get their own address. But if it's not a global variable, it's a local variable, or if it is an input to your function, you're going to find it on your stack. So you go to your stack, and you use this 1 that you have on a stack for temp, for TMP. Well, 1 is less than 2, so this if the condition for this if is met. So you go inside the if. Now we want to call function B. Right before we jump to B, we have to push stuff on the stack. So this B guy doesn't have any variable and doesn't have any input. So we don't need to push anything with that regard. But we still have to push the return address. So we want to say once we're done with B, we want to come back to this A3. So we push the return address A3 on the stack, and then we jump to function B. Immediately, function B wants to call C. So PC is here. Right before we jump to C, again, this C guy doesn't have any variables, doesn't have any inputs, so nothing there to be pushed, but we need to push the address. So the address that we want to return once we're done with C, we want to come to B2. So we push B2 on the stack, and we jump to C. Now the first inside C, we have another function call. So we're going to call A. Now, A does have input. So we push this number 2 here, and we push C2 as the return address on the stack. So we push temp equals 2 and return address C2. And then we jump to A. Now, inside A, we again see TMP, right? Where do we find the value? We find the value on the stack. So we look at the stack, the top of the stack. We see TMP2, and we use that. And well, 2 is not less than 2, so the condition is not met. So we're not going to go inside if. We go to printf. So this is like I'm emulating the command prompt. So we're going to print 2. What happens next? Next, we're going to execute return from A. We're going to return from A. A is done. Where do we go? So where do we go is dictated to us by what is on the stack. So I look at the stack. I see the return address is C2. So that's where I'm going to go. So next, I'm going to jump to C2. Now at C2, again, it's a return address. It's a return instruction. So I have to return from function C. Where do I return? Well, I look at my stack. I see what is stored on my stack. It's B2. So I'm going to jump to B2. Again, B2 is a return from function B. So where do I return? I look at my stack. I see I should go to A3. And that's what I do. Now I go to A3 and I print what is in A3, which is 1. Next stop is A4. And A4 is also a return from function A. Again, where do I go? I look at the top of the stack. It's ext. So I return to ext. Usually, when you see a stack growing, it's kind of like this, minus minus sp. So because as I said, we start from higher addresses with the stack and go down towards lower addresses. So high and then low. So we decrease the stack pointer. And let's say if I want to put something in it, I say, OK, first decrease the stack pointer. That grows, basically, that the stack grows downwards. That's why I'm doing minus minus. And this is, let's say this is a pointer. So I say in this location, write 2. So that's how a stack grows. And if I want to pop something from my stack, I do plus plus. This way I kind of pop from my stack something. So my stack pointer again goes up when you pop from it. When you push, it goes down. When you pop, it goes up. It's kind of vice versa. This is something that many people made mistakes winter 21 with regard to their stacks. So something to keep in mind. OK. Next stop, the third operating system concept, which you should be familiar with. It's called process. So processes are the third operating system concept that we're going to look at. So in a sense, you should be, you should have seen processes in ECE 252. Now, process kind of encapsulate the first two concepts. The first concept being thread, and the second concept being address space. So if I were to just define a process, it's an execution environment with restricted rights. So it's kind of a combination of one or more threads plus an address space and a bunch of other things like file descriptors, the file system context, and so on and so forth. Now, there's a fundamental trade-off between multiprocessing and multi-threading. And you should be aware of this as well. So you probably just know about it. In ECE 350, you're going to see why that's the case. But usually, when you have processes, you have better isolation. So two processes are kind of isolated. So it gives you kind of some notion of security, protection. So if you want to do something concurrently, but you want the processes to be isolated, you do multiprogramming. But it's a slow. So context switching between processes is a slow. Communication between processes is a slow. You probably remember inter-process communication in ECE 252. You have to file share or message passing or memory mapping, all of those techniques that you saw. It's time consuming. So communication between processes is hard. Context switching between processes is time consuming. Now, an alternative is basically multi-threading. So instead of having multiple processes, you can have multiple threads within your process. So one process, multiple threads. Now, this gives you a better performance because, as you will see, context switching between threads within the same process is faster and easier because threads within a process share a lot of things. So when you context switch, you don't need to change much. I'll go deeper into what I mean, but context switching between threads is easy. Communication between threads is really easy because they share the same address space. So anything within a process, all threads have access to, right? Even the stack of one thread is accessible by another thread. Although it's good, it's better, it's a best practice not to access some other thread's stack, but in reality, you can if you want to. So every thread within the process has access to the memory space of the process. So communication is easy, context switching is easy. This comes with a cost, and the cost is synchronization. So you don't get protection. So, you probably remember from ECE 252, you have to use locks and semaphores and, condition variables and all of that to make sure that, you have protected data that is not messed up by concurrent threads accessing it. And now let's get a little bit deeper into processes and threads. So this is something from ECE 252. Operating systems usually keep information about the processes in the PCB, in the process control block. They, store the unique processor identifier, program counter, registers, and so on and so forth. The memory pointers, I/O, the file descriptors, and so on and so forth. Again, you should remember from ECE 250. So these are all recalls. So I'm just putting them here to refresh your memory. There was this 7-state process life cycle that you saw. A process is either in init state or create, running, blocked, or finished. And then if you remember, we also added 2 other states for ready swapped and blocked swapped to take care of the condition where you don't have enough memory, right, to have all the processes in your main memory. So you have to swap one out to make some room, and then that guy becomes a blocked swapped or ready swap process. And this is just missing a bunch of transitions. For example, almost from all of these guys, you can go to finish. right? The other thing is you can be swapped right from running. So again, I'm assuming that you remember all of this. Okay, so what does it take to create a process? Well, operating system has to construct a new PCB when a process is created. This is usually inexpensive for the operating system to do. Some real-time operating systems like the one that you're implementing, although in the one that you're implementing, we have TCBs for task control block. We don't have a notion of process or threads. We call them tasks, and we have this task control blocks. But sometimes in real-time operating systems or embedded operating systems, you already have these PCBs statically allocated. Again, similar to the operating system that you're implementing. For kernel tasks, we already have these the PCBs. For user tasks, then you can either do it dynamically or statically. It doesn't matter. But this part, even if it is dynamic, it's not going to be a big of a deal for operating system to construct. So it creates a new one. It sets the initial values. It gives it a PID. It sets the PID. So it just sets up all the memory pointers that it has access to and all. So that's one thing. It's usually inexpensive. The second is to set up some page tables for this process. And this part is a little bit expensive. So this is where we are talking about address translation. So this part doesn't exist if your system is not using virtual memory, which is the case for your labs. So in your labs, everybody is just using physical memory, so we don't have page tables. But in general purpose operating systems where you have virtual memory, then you have to set up these translations. So you want the operating system knows the physical memory that is allocated to this process. So it has to kind of say how to translate or how to map from the virtual address space to physical address space. And we do this in page tables. We'll talk about these later in the course to just show you when, if you go to ECE 350, right after the reading week, we'll talk about address translation. So this guy is basically where we talk about page tables. So we'll come back to this like in the second half of the course. So this one is a little bit expensive from the operating system point of view. Then you have this, if you're forking your process, then you might think that the operating system should, let's say you had a really big process with a lot of memory footprint, and this process called fork. So one thing that you learned in ECE 252 is that when you fork, you create a copy of the same process. Now, a naive implementation is for the operating system to say, okay, wait, let me copy all this data in a separate location in physical memory and assign that to this newly created process to just create 2 copies. This would be super expensive because you're going to go to memory and copy a lot of stuff, and that's expensive. Usually operating systems don't do this. So this is the virtual, I'm saying V address space of P0. And let's say P from 0 to FFF. And let's say this guy created a copy of itself, and this is P1 from 000 to FFF, and these are identical, right? So these 2 are the same after the fork, except the PID. In the return of the fork is different in two. So they're almost the same. So let's say that this guy resided, now I'm looking at physical memory. So this was virtual. Let's say this is physical memory. And let's say this was mapped to somewhere here. Again, let's not talk about the sizing stuff. As I mentioned, a process doesn't necessarily need to use their entire address space. Let's say, some of it was used, and that portion that was used was mapped in this area. Now, as I said, the operating system could make a new copy and say, okay, this guy is mapped to this one. So that's one option. But this is a bad option because very likely this child is going to call exec, right? And then it's going to just change everything and then go and execute something else, right? So what's the point of copying a new process for this guy to be then, not used later on? So what the alternative is, let me actually switch back to my notes. That's easier to write. So far we were talking about this being physical memory, and let's say this is the area for P1 or P0, and then this is an area in the naive implementation. I might actually create a new copy for, so let's say this is P0, this is the virtual, and this is P1 virtual. So the naive implementation is to create another copy and then link it this way. Now, this is bad, as I mentioned. What happens, operating systems usually do this. Instead of creating a new copy, they make this guy to also point to the same physical memory. However, they set the access to this to read only. So initially, P0 had access to its physical memory, right, with write protected, right? Read and write. It could do read, it could write to its memory. It was free for P0 to do whatever it wants to its memory. Right after fork, we do something like that. So as long as P1 and P0 want to read from memory, operating system doesn't need to do anything. Everything is fine, right? The moment P1 or P0 want to write to memory, then operating system, this is read-only, so the hardware says, oh, nobody can write into this. It wakes up the operating system, and at that point, operating system creates the copy needed for this P1, which is usually after you call exec. So then you can, when needed, you can then do whatever you want. So this, for example, when you call exec, you might actually not want to copy P0. You might actually bring another image to the memory. So this is an optimization that operating systems usually do. So they wait until needed before they copy the content. So this has a name. It's called copy on write. So when you want to write, you make a copy. Before writing, you don't make a copy. So you just kind of what is it called? The term procrastinate doing this copying until it's really needed. It's like you have to now copy. Then you copy. Another thing for creating a process is to copy I/O state, basically file handles and etc. So this also is medium expense for the operating system to do. Okay, let me see if I can answer some of the questions that were asked. So could you explain what do you mean by statically and dynamically allocated PCBs? Right, so let's say you're writing an operating system for a satellite. And you know that this satellite in its life cycle, in its all its life, the moment you turn it on until it gets destroyed, is going to run 20 processes. You better know, actually, if you're writing a satellite, you're not going to dynamically create these processes probably. So you kind of know how many processes this satellite is going to run. So you can statically, when you compile your operating system, you know how many processes it wants. So you statically, it's kind of like variables in your kernel code, PCB1, PCB2, PCB3, and so on and so forth. So that's a static PCB allocation. So you basically hard code your PCB variables. Or the memory for them. But that's not usually the case for a system like Ubuntu, for example, right? In Ubuntu, like in a general purpose operating system, you really don't know how many processes you're going to create. In one run, you might have 10 processes. In another run, you might have 100. In another run, you might have 1,000. So it doesn't make sense to pre-allocate PCBs statically in the kernel code. So kernel then has to dynamically create PCBs. So it's kind of like inside kernel heap versus inside kernel static data. So because PCB has to be in kernel memory, don't forget. PCB has to be in kernel memory. Now the question is, do we want to have these PCBs statically allocated? Like in the kernel code, we say, we define the struct PCB, and then we say a PCB array of 20. So I know that I only need 20 PCBs. So here is the array of 20 PCBs. Or I don't know how many PCBs I need, so I will just allocate them in my heap whenever a new whenever a new process is created. I do allocate in kernel heap, and then I, allocate enough memory to store a new PCB. Okay, so hopefully that answered the question. Okay, so with a fork, is a new PCB created? Yes. So you create a new PCB and you give it a new new ID. So just a little bit of detail here. I just, broadly said the entire memory they point to. It's not the case, right? In reality, your process has different regions, right? So some of these regions you copy, some of them you don't copy in copy to write. So it's region based. Again, we'll talk about it later. So I just, very broadly said the entire memory. But something like PCB, yeah, okay. Another question with a fork. Yeah, a new PCB is created. Yes, with fork. So for copy on write, if the original process wants to write to memory, will the OS allocate new memory for the original process or for the forked process? Doesn't really matter, but for the forked process, yeah. So you give back the original memory to the parent, and you create a new one for the child. It doesn't really matter, right? The fact of the matter is that you're going to create another copy and give it to one of them. They're almost the same. But practically, it's you give it to you create a new one and give it to the child. Okay, thank you. Okay, but most times when we create process, we change the existing memory one way or another. So why not just create a new memory for every fork? As I said, let's actually, I think I have a slide. So your memory is you have sections of your memory, right? You have this code, you have heap, you have a stack, and so on and so forth. So it's not a monolithic memory, like just big chunk of memory that you have. So each process has different chunks of memory. Yes, some of them, you know, when you segment your memory, then it's easy. So you can say those segments that you're not going to change, so you don't change them until you want to change them. So they share. The segments that you have to create 2 copies, you create 2 copies. But the point is, you don't create 2 copies of the entire thing at the beginning. So you probably duplicate some of the segments, but the rest of the segments, you make them share, something like that, right? So that's the point I was making, that it's not a monolithic, like a big chunk of memory. It's usually segmented or paged, if you wish. So for some of those pages, you do duplicate from the beginning. For some of the pages, you wait to see what happens, and then if needed, you duplicate. Okay. Now, one of the things that I mentioned, and based on experience, I think you don't know, or you might know, I don't know, from ECE 252, is that, as I mentioned, threads actually have access to the entire memory address space. So they can touch anything they want, including the stack of other threads, right? Let me actually go up here to mention something. So let's talk about this one. So this is a PC. This is a picture that you probably have seen from ECE 252. Each thread gets its own PC, right? Its own stack, its own registers, but then they all share the code, they share the data, they share the files and all, right? The fact that each thread has its own registers and PC and a stack doesn't mean that another thread cannot touch these. They can. So it's just we have multiple copies of, sorry, multiple stacks or stack pointers, but all threads can access anything within the process address space. Now, right. So this is just kind of definition. It's not important. This is slide. How did I jump to that? Okay, so I think I kind of explained the trade-off between multi-threading and multi-programming. So we talked about all of this. We talked about communication being harder between processes and being easier between threads within the same process. Okay, now let's talk about what are the ways, if we want to kind of, so let's first talk about a stack allocation. Let's start with that. So if you have one thread in your process, then it's easy, right? A stack starts from top, comes to bottom, heap goes upwards, everything is fine. Now, what if I have 2 threads? So each one of them is going to get in a stack, and their stack is going to come down. So now let's say for the first one, let's go here. So this is my virtual address space. I'm going to put the stack of the first one here, stack of T1, and it's going to grow this way. Now, where should I put the stack of thread 2? You will soon realize that at some point you have to just say, okay, I'm going to put the stack of thread 2 here. And this means that if thread, because there is no other space to put it, right? The bottom is occupied, and then where else to put it? You're going to put it right below the stack of T1 with some free space. So this is the space that a T1's stack can grow or shrink. But then you have to be careful, because if T1, like, a stack overflows, the stack of T1 overflows, then it could come and basically mess up with the stack of T2. And the same with T3. I'm going to put the T3 stack here, stack for T3. So if T2's stack overflows, then it's going to come and destroy a stack of T3. So going back, so this is how we're going to put them. So we're going to put a stack of stack 1 at top, and then put some space, and then put a stack T2, and then some space stack T3, and so on and so forth. But then there is always a chance that a stack of T1 overflows to a stack of T2, or T2 to the stack of T3, and so on and so forth. And usually operating systems say, it's not my job to protect these stacks from each other. So usually operating systems are going to say, this is your address space, use it the way you want. Any thread within the process can do whatever they want. Now, a question that arises is, how much space should we put between the stacks? In a 64-bit system, you have a lot of memory. So you have, I don't remember, I think it's in one of the Piazza posts I mentioned, it's 2 to 60 something gigabyte of memory. So like it's mind blowing how much memory, how much virtual memory you have. So you can allocate as much as you want, right? You have almost infinite amount of memory. So you can put megabytes, gigabytes of memory for each stack, and things will be safe. But so that's about user processes, right? But within the kernel, you might also have threads, kernel threads. So your own kernel could be multi-threaded. And you usually, as we talked, we want to make the memory footprint of operating system as small as possible, right? Because operating system usually uses physical memory, right? It's operating system, so it doesn't want to do. It's kind of different than processes. So you allocate a small memory, a small physical memory to operating system. So it's kind of important for operating system threads to then be careful of their stacks. So usually, kernel level stacks in x86 are very small, like 8 kilobyte, and they have to make sure that they don't overflow to each other, the kernel threads. So you shouldn't have like a recursive call or something like that. It's detrimental. You can mess up your kernel. And again, as I said, for user level stacks, it's not a big deal usually, right? Because we're talking about virtual address space, and we have a lot of it. If they violate, as I said, well, they can just mess things up. Is there a way to at least catch that this happened? Like if we were to just catch that a stack overflow happened, then the answer is this: yes, we can. One technique that is used is for the operating system to put some data here, some flag or something. And if this stack overflows, it will overwrite this data. Now, every time you context switch between threads, you can check this data. If it is not changed, then with high probability the stack hasn't overflown. if this data has changed, then with 100%, you can say, okay, a Stack Overflow happened. So one thread went to another thread because this data meant to be not touched. And if it is touched, it's very, very probable that one stack went down to another stack. So that's kind of, you can detect that this happened, but that's all the operating system can or will do. Because if operating system wants to actually enforce isolation between threads, then threads become like processes. What's the point, right? We really don't want to get into the business of threads. We want to let them do their thing freely. Okay, so let me answer questions that are asked. When you call fork once, will both the parent and child process share the same data in memory as read-only until a write request is issued? As I mentioned, probably not all the data is the same. You probably make some data different, but bulk of the data, yes, you keep them the same until one of them writes. Threads share the same heap, yes. All threads share the same heap, so you don't need to have different heaps for different threads. Each thread that calls alloc gets a pointer from the processes, the processes heap. So all of them share the same heap. Kernel level means total stack space on the OS, or do you mean one kernel thread? So what I mean here is you have kernel memory. So there is you on your physical memory, but some of it is allocated to kernel, right? And usually kernel uses that for itself. That's kernel memory, and it's limited. Now your kernel could be multi-threaded. So the kernel itself can have multiple threads to do stuff, right? You might not want to do everything in one thread in operating system. That wouldn't be a good idea. So if you have kernel threads, all of them are sharing this memory together. So then in that case, you want to allocate a stack to each one of those threads, and you have a limited space. So you basically, this is a norm. Each one of them gets about 8 kilobytes of a stack. Hopefully that explained the point kernel level here. Is there some way the compiler can determine what the max stack size of a program is during compilation? If so, couldn't the compiler save? No, the compiler, like if you have a recursive call and the number of recursions depend on the input, then compiler has no idea how many times the function will be called. So the compiler has no means to know how much a stack your thread will need, right? It will be determined at runtime. If a process has some threads and then we call fork, then do we create a copy of the threads as well? Given that there are some write operations before anything returns. When a process calls fork, the entire process forks with its threads. So I hope I answered that question. Does that make sense? What is meant by context switching? We'll talk about context switching in a lot of details in coming slides. Okay. Okay, so multiprogramming. This is a way to run multiple processes. So whenever we're talking about multi-threading, we're talking about one process having multiple threads. whenever we're talking about multiprogramming, we mean that the operating system is running multiple processes, which is usually the case. And this basically shows you very, very high level what multiprogramming means. So for each process, the operating system brings its data, like stack, heap, data and code to memory, and that's how they can run. And any process gets to use its own virtual address, right? That is mapped to somewhere in the physical address, right? So process 1 has virtual address 0x, 001, for example. This guy also has a virtual address 0x001. This guy also has a virtual address 0x001. Now, the 001 in P1 is kind of mapped here in physical memory. The 001 is mapped here in physical memory for process 2, and it's mapped here in physical memory for process N, right? So each one of them has its own virtual memory space, and we map those to physical memory, and that's how it's done. Now, here comes the question somebody asked about context switching. How do we multiprogram in a system that only has one CPU? So if I have only one CPU, this means that I can at any given time only run one process. So how do I really multi-program? And the answer to that is you time share. It's very similar to the discussion we had about time sharing operating systems. We're revisiting it. How do we kind of create this illusion that all the processes are actually doing something? It's kind of like, let me see if I can find a video or something. I bet there are these chess masters playing with a group with playing multiple games. Yeah. So if I look at the video, like an image of this, yeah, it's kind of like this. So there's this chess master. So each one of these chess players here sitting is kind of like a process. And this chess master is the processor. And it comes, makes a move with this one, and then goes, makes a move with the next one, and goes and makes a move with the third one, and then comes back to the first one. Does it? And it's kind of like each one of them feels like they're playing a game, right? But they're basically time sharing the chess master here. So, and that's pretty much like processor and processes. So this CPU here is kind of like the chess master, and then there are processes here. So it goes to process 1, it executes some of its instructions, and then it goes to process 2, it executes some of these instructions, and then goes to process 3, executes some, and then comes back to P1, P2, P3, and then rotates, right? Something like that. And then it's as if each one of them is making progress all the time, right? So there is this illusion that as if like there are as many chess masters as we have players, but in reality there is only one, but it's time sharing between all the chess players. So in reality there are, few processors in a system. Let's say you have a multiprocessor has 4 processors, and then you're running 400 processes, right? And in the picture that we saw last time, you might actually have 2,000, 3,000 threads. So when you're working with, right now I'm working with my system, there are hundreds of processes running, right? But my system has only 4 processors. But we are feeling that all these processes are running, and that's achieved by time sharing. So the processor time is shared between all these processes. I'm using, I'm using QuickTime, I'm using Microsoft Teams, I'm using my PowerPoint, and so on and so forth. All these processes at the same time, and I only have 4 processors. The way it's done, I think I have 4 processors. At this point, I don't remember 4 or 8. But anyhow, so it feels like all those processes are making progress. The way it's possible is by time sharing the CPU, the processor, and that's basically the what we will talk about. Basically, the operating system is the one who decides which process to run, how long to run that process, in which order, and so on and so forth. So we'll come back to this basically the topic of scheduling processes on the processor in few lectures from now. So we'll talk about scheduling in details. Right, so we talked about this. So this is the time. It's basically divided between processes. Now, the question is, so here we context switch. This is context switch. So we were running process 1, and then we context switch to process 2. Then we context switch to process 3. And at some point, we context switch to process 1, and so on and so forth. Now, what triggers these switches? When do we context switch? Now, what triggers context switch is one of the 3. So 3 things could cause context switching, which we'll talk about in the next concept. So there is the interrupts, like a timer interrupt, right? There is the system calls, like for instance, you say read from a file, and this is a system call, and maybe operating system has to go and bring the file. So this is where operating system might decide to put process 1 into waiting, and then context switch to process 2. So that's the second one. So first one, interrupt. Second one was system call. The third one is exceptions. So let's say your process accessed a memory location that it wasn't supposed to access. So at this point, we're going to probably kill your process and context switch to some other process. Or maybe your process divided by 0, right? So when an exception happens, segmentation fault, page fault. So with the exceptions, you might actually have a context switch. So these are the ones that trigger a context switch. We will talk about them in more details as we progress. Now, before actually touching on those topics, let's talk about what is necessary, very high level, in terms of time sharing. What do we really need? I mentioned the first one being a scheduling. So we should have a mechanism to decide who runs first, who runs second. Now this becomes your P2. So in P2, you're going to implement a scheduler. What do you think? Was it P2 or P3? Yeah, I think it's P2. So in P2, you design a scheduler. So you basically design how you identify the next process to be executed. The second thing that is needed for multiprogramming is protection. You need to protect processes from each other. If you are to timeshare, you want to really protect processes from each other, and you also want to protect operating system from the processes. So I got a bunch of questions. It might be a good place to stop and answer those questions. So is time sharing also true for threads within the same process? Yes, I mean, as long, so if you have one process, one processor, then if you have, one process with 10 threads, at any given time, you can just run one of those threads. So you're time sharing the processor between those threads. So it's correct between threads as well. So we're time sharing. Still didn't understand voluntary yield. So where was it? So when a process calls pthread yield, it kind of tells the operating system you can context switch to something else. So if a thread says pthread yield, let's say you have one process and this process has one thread and that thread calls yield, that tells the operating system that you can schedule something else. Now the operating system could or could not. It depends on the operating system. It depends on other processes or other threads in the system. Do we want to context switch or not? So, and by the way, yield is kind of like a system call, right? It's a system call. It's a service provided by the operating system for voluntary context switches, where one thread says, I'm done for now. Put me in ready and run something else if you have anything else to run. So it's voluntary yield. Aren't exceptions a special type of interrupts? Yes. So let's put it this way. In many textbooks, exceptions are just called interrupts. The reason we give them different separate names is because interrupts are exogenous, like they come from outside. Whereas exceptions come from inside, like divide by 0. Your program does something that causes exception. You divide by 0, you access some memory that you were not supposed to do. So it's kind of like internal versus external. Interrupts are external. Exceptions are internal. Again, we have slides on these two, but usually people call them exceptions or interrupts, both of them, right? When the CPU context switches, how does it actually check the stack space? Which stack does it check? I have slides for you. We'll talk about it, actually. Okay. So very quickly, we talked about scheduling. So when you want to schedule, there are certain things to pay attention to. Like do you want to be fair, for example, between processes or between threads? Do you have some real-time constraints to meet? For example, if you have deadlines, then you want to meet those deadlines. So are you, do you care about, for instance, latency? Are you streaming? So there are a bunch of criteria when it comes to scheduling, and this is something that we'll talk about in details. In very high level, scheduling is like this. If you look at the ready processes, you look at the list of PCBs. If you have one ready, you select it. This select process is kind of where you do the scheduling with some criteria, priorities, deadlines, whatever. You choose a PCB and you run it. And then if there is no process to be run, then you kind of run idle until you have something to execute. And you just continue this. Okay, I think this is a good place to stop. I was hoping that I get to talk about other stuff, but unfortunately I couldn't. Okay, so that's fine. Yeah, thank you for those of you who attended the lecture, and thank you for those of you who are watching the lectures afterwards. I got a question. So if you want to log off, log off. So let me answer this question. Is deadlock detection a recovery part of a scheduling tool? Recovery part of a scheduling. I don't understand the question actually. Is deadlock detection? Oh, is deadlock detection and recovery part of a scheduling tool? Not in this context. In the here by scheduling, all I mean is the order of processes to get to run on the processor. Deadlock detection is a separate issue than a scheduling. Okay, so thank you. Take care. Be safe. Talk to you on Tuesday. Or actually tomorrow. There is going to be a tutorial. Take care. Bye bye.